Welcome back. Today we're going to talk about two new concepts, which are observability and minimality. Okay? So, in particular, how this lecture is going to go, we're going to start off by kind of defining and motivating observability. After we do that, we're going to talk about observability for LTI systems, and then we're going to finish up by talking about minimality. Okay? All right, so let's get started with point one, which is defining observability. Okay? So I want to begin with a little bit of motivation as to what observability actually is, okay? So, remember kind of in the previous lecture, what we had done is we had discussed this idea of fundamental limitations on control systems, right? We kind of did this through the lens of controllability, which says, okay, there are certain fundamental limitations that tell me which states I can reach and which states I cannot reach, right? So we talked about controllability, which is can reach some states, maybe not others, okay? This was kind of all wrapped up in the idea of controllability. Okay, so this was one example of a fundamental limitation on a control system, right? Maybe we could get some place in our state space, but not to some other place. So what we're going to do today is we're going to talk about another fundamental limitation. That limitation is observability, all right? So you might remember one of the important properties about controllability is that it only was a property of state, right? Not a property of output. So not of output, okay? So controllability was really only focused in transferring states between different positions, okay? So this said nothing about the readout map or our output space or anything like this, okay? So observability is a fundamental limitation that has to do with these outputs, all right? So observability focuses on outputs. Oops. That didn't come out right. There we go. My gosh. All right. So in order to kind of motivate what observability is, I first want to talk a little bit more about what outputs are. Okay, so we kind of defined what outputs were all the way at the beginning of the course, but I want to go back and kind of revisit them and make sure we kind of know what they actually are. All right. So outputs will generally represent two things. Okay. So one of the following. Either one, they'll represent a quantity we want to control. So for example, if I have like a little robot system, which I'm kind of moving around, and I want to control the position of the robot, say the state is x and its velocity v, then maybe the output would be position x, right? Because I want to control position. All right, so that's one thing that an output can be, right? It can be the quantity that we kind of want to control in our system. Now, what else can it represent? Well, it can represent quantities we can measure, all right? So let's say we have some sensors that are taking measurements of our system. Oftentimes, it's not going to be the case that we can kind of measure our entire full state vector, right? We're usually only going to have kind of partial measurements, right? So let's say, I don't know, I take something like a little quadcopter drone that's flying around, right? Maybe I know its position and orientation measurements, right? Let's say maybe I have some like motion capture system that's giving me position and orientation, but maybe I don't have everything else, right? Maybe I don't have a good immediate measurement of, say, like velocity or angular velocity, okay? So this is what we're going to kind of focus on with observability. All right. Observability is going to focus on the relationship between measurements of the system, which are the outputs, and the state of our system. Okay. So a really important question in control, key question, is can we reconstruct our full state vector from partial measurements or partial observations? Okay. So let's say, for example, I'm only able to measure the position of my system, and I get some, position signal over time. Would I be able to construct my full position and velocity state vector, right? So this is kind of what observability deals with. So this is the realm of observability. Okay? So we kind of say that a system is observable if we're able to reconstruct our full state vector from any sort of, sequence of measurements that we want. Okay? So we're going to kind of make this idea a little bit more precise momentarily. But first I want to run through just a quick example of a system that's not observable. All right? So we kind of get a clear idea of what we're talking about. So let's go ahead and consider the non-example. So let's say I take a system with dynamics x dot equals 1, 1, 0, 0 times x plus, let's say, 0, 1 times u. Now I'm going to be interested in the output as well, right, because we're talking about observability. So let's say my output equation is y equals 1, 0 times x, okay? So my question is, can I reconstruct my full state x from measurements or observations y? Okay? So take a moment to think about this, okay? Just kind of take a close look at the structure of this system. All right, so I'll assume you gave this some thought, right? And maybe the answer that you came up with is no, right? So we see that the first component of x, which we'll call x1, and the second component, x2, are entirely decoupled, okay? Entirely decoupled. All right? Now further, we only measure x1, right? Because this only goes ahead and just pulls out the first component of my state vector, right? So the basic problem here is that we have two different components which are entirely separate from each other, and we're only measuring one of them, okay? So if we get measurements of one, that tells us nothing about what's happening with the other, all right? So this is an example of a system which is not observable, all right? Pretty clearly, no matter how clever we are in designing some sort of estimator, we won't be able to figure out what the second component of our state vector is doing, only given information about the first component, all right? Okay, so now that we've kind of sketched out this basic idea of observability as, being able to reconstruct our state vector from partial observations, let's go ahead and actually start putting some more math down to this, okay? Let's try to be a little bit more precise. Okay, so my next question is, how do we make these ideas precise? Okay, so there's a kind of nice idea, which is, if we're trying to reconstruct the state vector for all time, maybe it's just sort of sufficient just to know what my initial condition was, okay? So here's a basic idea. If I want to reconstruct my full state trajectory, which I'll call x of t, from knowledge of y of t, which is my output, and let's say we have knowledge of my input as well, and u of t. Say we know these on an interval 0, t. It's enough to be able to reconstruct my initial condition, right? If I'm able to reconstruct my initial condition, then I can kind of figure out what my trajectory of the state was for all time, okay? Kind of by existence and uniqueness. All right? So the basic idea of observability is we're going to say, okay, if we could find some input signals out there that kind of distinguish between different initial states, then we should be able to kind of figure out where our system came from, okay? So I'm going to write this down first through a concept called distinguishability, and then after we've done this, we'll come back and talk a little bit more about observability, all right? So let's first set out this preliminary definition, which is distinguishability. And this effectively tells us about the idea that, if we could find if we could find an input signal that kind of picks out the difference between two initial states, then we could work out which initial state we actually came from. Okay, so this is distinguishability. So again, I'm going to state this definition for an abstract dynamical system, and then we'll kind of specialize a little bit later. All right. So let's say consider an IO dynamical system, which I'll call D. It's going to have an input space U, an output space Y, state space sigma, state transition map phi, and readout map R. All right. Let's say we also have a time set T and IO map rho. Okay. Now remember, the IO map rho was just that kind of convenient composition of the readout map and the state transition map, right? It just kind of goes directly from initial state, input in a pair of times, to your output value at the end time. Okay. All right. So what I'm going to do is I'm first going to define what it means for a signal to distinguish between two kind of initial events. All right. So remember from last time, what we had said is an event is a pair of a state and a time. Okay. So first, I'm going to define what it means for a signal to distinguish between two events. So what I'll say is let t1 be greater than or equal to t0, and x0 t0, and x0 hat t0 be events, right? Pairs of a state and a time. All right, so I'll say that signal u, which belongs to my input signal space u, distinguishes between these events. Distinguishes between x0 t0 and x0 hat t0 hat, or excuse me, t0 at time t1, simply if the values of the outputs are different at time t1. Okay? So if I have rho of t1, t0, x0, an input signal is not equal to rho of t1, t0, x0 hat u. Okay? So we say that this signal distinguishes between these two events if, at this time t1, the outputs from these two different initial conditions are actually different. All right? So because of this, we say that this signal is distinguishing between the two of them, right? The signal picks out the fact that these two initial conditions are in fact different. Okay? All right, so that's what a distinguishing signal is, all right? Now let's talk about something a little bit more general, okay? So I'll say let t1 greater than or equal to t0. Now the events x0, t0, and x0 hat t0 are distinguishable if there exists a time t in t0 t1 at which some input signal distinguishes between them. All right, so we say that x0 t0 and x0 hat t0 are distinguishable on this time interval t0 t1 if there exists an input satisfying condition 1 up here. All right, so condition 1 says what it means for an input to distinguish between two events. It means that eventually, right, at time t1, the outputs will be different. And point 2 over here says what it means for two events to be distinguishable. All right, two events are distinguishable if in this time interval we can find an input that distinguishes between them. Okay, so let's go ahead and bring this back to this idea of observability, right, which we had kind of said was, having to do with the ability to reconstruct our initial condition from output and input data. All right, so it brings us to formal definition of observability. All right, so again, we're going to consider an IO dynamical system. So consider an IO dynamical system D on a time set T, okay? So I'll say that the system is observable on the interval t0, t1, which is a subset of t, if for every distinct pair of states, okay, so states that are not equal to each other, x0, which is not equal to x0 hat, belongs to my state space, the events x naught comma t naught and x naught hat t naught are distinguishable on the interval t naught t1. Okay? So basically what observability is saying is that, okay, for some time in this interval t naught t1 in any pair of states, I can always kind of find an input to distinguish between these two states. All right? So if I give you two different initial conditions, x naught hat, I'm saying that I can find an input and a time in t naught t1 where the outputs from these states will be different. Okay? So I can always kind of find an input signal that picks out between two states. All right? And from this, I can kind of reconstruct where my initial state actually was. All right? So if I say I hand you two different initial states, right? Then I can actually kind of separate those two states from the output perspective with one particular distinguishing input. All right? So you might be asking, all right, well, this seems like a kind of tricky condition to satisfy, right? Because I'm saying for any two pairs of states, I need to be able to find one input, right? It's not going to be an input that works for any pair, right? I'm giving you any pair, and then I'm finding an input specific to that pair. You might be asking, okay, can we sort of do this output separation this initial state separation for any given input signal? It turns out for the class of LTI systems, yes, all right? So we'll kind of talk about this a little bit later, but you should just know this is going to work out pretty nicely in the LTI case, all right? Okay. So with that said, I just real quick want to talk about observability for abstract time invariant systems, and then after that we'll talk about state space representations in particular. All right? So it's a kind of nice consequence of time invariance that if we're observable on one time interval, we'll be observable on a shifted version of that time interval. Okay? So I'm just going to state that as a proposition. So proposition, this is observability for time invariant systems. So I'll say consider a time invariant IO dynamical system D, and let's say the system is on a time set T. All right? So what we say is that if the system is observable on the interval t0 t1, then for all little tau belonging to my time set t, the system is observable on the shifted interval. Okay, so t0 plus tau, t1 plus tau. All right, and the proof of this is just a direct application of the definition of time invariance. All right, so remember, if an I/O system is time invariant, then its I/O map really doesn't depend on shifts in time, right? So because of that, if we just take the input signal that distinguishes between two states and we just shift it by the time tau, then that'll distinguish between the two states at tau seconds later. All right? So you can go ahead and work out the details of this, but this is a fairly straightforward result. Okay? All right, so that's the basic idea of observability for these very general I/O systems, right? We kind of have this idea that if we have any two initial conditions in our state space, I can find an input signal that kind of picks those two conditions out, right? That distinguishes between them at some time, right? So this is this abstract idea of observability. Now I want to go ahead and I want to specialize to the case of linear time invariant state space systems, okay? So that brings us to our second point for today, which is to observability of LTI state space representations. Okay? So this is kind of the same path that we took with controllability, right? First, we stated this very abstract definition for dynamical systems, and then after we did that, we said, okay, let's go ahead and let's take a look at the LTI case where we have a nice state space representation that we could say a whole lot about, right? Let's do the same thing here, okay? So now what we'll do is we'll take a look at observability of the LTI state space representation. X dot equals AX plus BU, right? That's the state equation. And then Y equals CX plus DU. This is the output equation, all right? So I'm just going to focus on the continuous time case, just for the sake of time in lecture, okay? But you can also do this for the discrete time case, and as usual, all of the analogous results will hold, okay? So you need to be a little bit more careful about your time interval in the discrete time case, but outside of that, all of the theorems will look more or less identical, okay? All right, very nice. So what do we want to do? What's our goal? Well, what we did with controllability, right, is we kind of found some really nice, sharp algebraic characterizations of controllability, right? We found that controllability on one time interval was equivalent to controllability on any other time interval, right? So we kind of want to see if we can get some analogous results for observability, right? So what we want is we want a sharp algebraic characterization of observability, something that's really easy to compute, right? And we want to see if we can get observability on any time interval, okay? This is kind of what we had in the continuous time case, right? I said I can get controllability on 0, t for any t greater than 0, right? Maybe I could do the same for observability. Okay, so how are we going to set this problem up? What are we going to do? Let's kind of sketch out a basic problem setup. So let's see if we can make any simplifying assumptions to make observability a little bit easier to study, right? Well, first, as a kind of result of this proposition, right, since, observability on one time interval is the same as observability on another, what we'll do is we'll just study observability on intervals of the form 0, t, right, for some t greater than 0. Because basically, if I shift this by any time t in R, I can kind of reach an arbitrary interval by this time invariance property over here, right? So that's the first thing that I'm going to do, all right? Now, with this in mind, let's kind of set up a basic observability problem, all right? So I'll say, suppose we're given the values of the output signal y and input signal u on this interval 0, t. And, we're going to assume that we know all of our system matrices. We know A, B, C, D, okay? So what are we going to do? What we're going to do is, kind of in the spirit of this observability problem, is we're going to try solving for our initial condition, x0, based on this data, okay? So I give you y, I give you u on this interval 0, t. Now I want to work backwards to figure out where my system started, all right? So let's see how we might do this. Well, first what I'm going to do is I'm going to kind of just write out the definition of the I/O map, right? So I know that for all time t in 0, t, I'm going to satisfy y of t equals c e to the at times x0 plus the integral from 0 up until t, c e to the a of t minus tau, b u of tau, d tau, plus du of t, right? This is just the formula for the I/O map, okay? Now, let's kind of isolate the unknown part, right? We know that this is the only thing that we don't know, right? This entire term over here is known, right? We know c, we know e to the a t minus tau, we know b, we know u, we know d, okay? So let's bring all the knowns to one side, and let's bring the unknowns to the other side, okay? So if I do that, what do I get? Well, I'll get y of t minus the integral from 0 to t of c e to the a times t minus tau, bu of tau, d tau plus du of t. Okay? And that's going to equal c e to the at times x naught. All right? So what I want to do is I want to solve for x naught. Okay. So let's kind of clean this thing up a little bit. Where kind of might we start if we do this? Well, we kind of notice that the entire signal on the left-hand side is a big known quantity, right? So let's just kind of hide this whole signal behind some blanket, which I'll call y hat of t, right? So what we're really trying to do is we're trying to solve y hat of t equals c e to the at times x naught, okay? Let's just suppose for convenience y hat is differentiable, okay? We're just kind of sketching out a basic idea right now, okay? So we can kind of make any assumptions that we want just to kind of make this problem a little bit easier. Okay, so we're assuming y hat is differentiable, right? Now what do we do? Well, what we're trying to do is we're trying to figure out a sharp algebraic characterization for observability, right? We're trying to figure out a really nice algebraic way to solve for x naught. So what I want to do is I want to see if I could get rid of this matrix exponential and replace it with just some algebraic terms, okay? So how are we going to do that? Well, let's go ahead and try differentiating both sides, and we'll see where that takes us. So if I take the ith derivative of both sides, y hat of t equals d dt I c e to the at times x naught, and I kind of work out this process, what I'll find is that I'll get c times o to the I e to the at x naught is equal to the ith derivative of t, okay? Ith derivative of y evaluated at t, all right? So now let's go ahead and let's evaluate at time t equals 0. What I find is that yi at 0 is equal to ca to the I times x naught, okay? So now if I go ahead and I evaluate a whole bunch of these, right? Then I'll get a system which kind of looks of the form. So let's say my first derivative, or my 0th derivative of 0, okay? That's going to equal ca to the 0, which is just c times x naught. My first derivative is going to be ca times x naught. It's going to keep going, right? And as a result of the Cayley-Hamilton theorem, right, which remember from last time told us that after we go beyond power n minus 1 of a, we don't really get any new information. The best we're going to do in terms of solving this system is going to be n minus 1 derivatives, right? Because after n minus 1, any higher power of a becomes a linear combination of the lower powers, okay? So n minus first derivative at 0 is equal to ca to the n minus 1 times x naught, right? We pull all this out, we get c, ca, all the way down to ca to the n minus 1 times x naught, okay? Now, since we know our since we know our output signal, right, this entire left-hand side is known, right? Now, this matrix on the right-hand side is also known, right? We assume that we knew A, B, C, D, okay? So basically, if we can solve this resulting linear system of equations, right, which is just a standard linear algebraic system now, right, nothing more, then we can reconstruct x naught, okay? So if I'm able to find a unique solution to this equation, right, then I'll be able to figure out what x naught actually was, all right? And this is only using data of my output and my input signal, all right? So this basic kind of sketch of a strategy leads us to something called the observability matrix of the system, right? It turns out the observability matrix is going to be exactly this matrix that we defined over here, okay? So the idea in this case is, well, if this matrix is full rank, we'll be able to solve this system, right? So that gives us really nice, sharp algebraic condition for observability. Okay, so let me write out this theorem regarding the observability matrix, and then we'll go ahead and prove it. So this is the observability matrix. All right, so let's consider an LTI state space representation A, B, C, D. Okay, I'm just going to assume it's continuous time for now. Let's say A belongs to Rn by n. Then the following are, let me rewrite that G. There we go. Are equivalent. Following are equivalent. So first, what I'm going to say is observability. Okay, this is going to be our first condition. Observability. And what I'm going to say is on any interval, T naught T1, which is a subset of R, with T naught less than or equal to T1, or strictly less than, excuse me, the system is observable. What I'm going to claim is that this is equivalent to that matrix up here being a full rank. Okay? So condition 2, observability matrix. So I'm going to say that the observability matrix, which I'll write OAC, since O for observability, and AC, since it depends on A and C, this is equal to C, CA, all the way up to CA to the n minus 1, where n is the dimension of the A matrix. This matrix is a full column rank. Okay? So my claim is observability is one-to-one with this observability matrix being full rank. Okay, nice. So let's go ahead and prove this result. Okay, fantastic. So, proof. First going to start out by showing that 1 implies 2. Okay, so I'll say that assume the system is observable on any interval, which I'll call T naught T1, subset of R, with T naught less than T1. I want to show that this observability matrix is going to be full rank. Okay, so first what I'm going to do is I'm just going to pick a nice interval. So I'll pick an interval 0, t, with some t being greater than 0. Okay, let's try to prove this thing by contradiction, right? So let's suppose for contradiction, OAC is not full rank. All right, now what does that mean? Well, that means that there exists some vector in its null space which is non-zero, right? So then there exists a v which is non-zero such that OAC times v equals 0, right? That's what it means to not have full rank. Let's kind of expand this condition out. So what we have is C times v, CA times v, all the way up to CA to the n minus 1 times v equals 0, right? So this implies CA to the I times v equals 0 for I equals 0 up until n minus 1. Okay, so here's the basic idea. What we're going to do is we're going to show that if we pick an initial state of v, we won't actually be able to distinguish it from some other states in our system. All right? And using that, we're going to get a contradiction with the definition of observability. All right, so let's study the output from initial condition x naught equals v. Okay? Now, as a result of the Cayley-Hamilton theorem, what we have is CA to the I times v equals 0 goes ahead and implies that C times the exponential of AT times v equals 0 for all t in R, right? Because remember, the Cayley-Hamilton theorem tells us that if the first n minus 1 powers have this property, where CA to the I times v equals 0, then we're going to have that property for all n. If we have that property for all n, that means that the matrix exponential needs to vanish, right? Okay, so that's what the Cayley-Hamilton theorem tells us. Let's use this fact to compute the output of our system. So we have a row of t0v, and any arbitrary input signal u is equal to ce to the at times v plus the integral from 0 up until t of ce to the a t minus tau bu of tau d tau, right? Since we have cx of at times v equals 0, this is simply equal to the integral from 0 to t ce to the a t minus tau bu of tau d tau. But what's this equal to? Well, this is equal to the zero state response, right? To this arbitrary input u that we picked. So this is equal to rho of t 0, 0, u. So what's the problem here? Do we have a contradiction? What we have is, for any input and any t belonging to this interval 0, t, we have rho of t0 v u is identically equal to rho of t0, 0 u. So this means we cannot distinguish between v and 0 as our initial conditions, okay? And since we assumed v is non-zero, right, since we used it to get a contradiction with full rank, what this means is that we now have a contradiction, okay? So then we conclude OAC must have been full rank. All right, fantastic. So let's kind of outline the argument once again. We said, assume for contradiction it's not full rank. That means there exists a vector v that's in the null space of my observability matrix. If this vector exists, then it needs to satisfy cx with at times v equals 0. If I go ahead and I take that as my initial condition, that means that I get the same zero state response, or excuse me, the same output as the zero state response, okay? And effectively that means that, since that holds for all u, I cannot distinguish between this initial condition v and the 0 initial condition. Now, since there exists a pair which I can't distinguish between, my system can't be observable on this interval, and that contradicts my assumption. All right? It's a kind of intricate argument here, but it gets the job done, right? All right, fantastic. So let's go ahead and prove the other direction. So 2 implies 1. This is already more or less what we proved above, right? But I'll kind of just resketch out the argument real quick. So what I'll say is, fix a pair of times t0 less than t1. And we assume OAC is full rank. What we want to show is the system is observable on t0, t1. Okay? So that means that for any pair of states, starting at t0, I can always find an input signal to distinguish between the two of them, right? Okay. Well, what do we know this is equivalent to? Well, because of time invariance, we know that this is equivalent to observability on 0, t1 minus t0, right? If I just shift both times by a minus t0, okay? And I'm just going to define this to be equal to 0, t, okay? So I'll define t equals t1 minus t0. So just kind of clean up our notation. All right. So now what I'll do is I'll consider the 0 input signal, which I'll call u, which is equivalent to 0. Now, for an initial state x0 belonging to sigma, what this means is that my output will be of the form y of t equals c e to the at times x0, right? This holds for all t in 0, t. Now, if I do this differentiation argument, what I'll find is that y at 0 all the way until the n minus first derivative at 0 will equal to c all the way until ca to the n minus 1 times x0, okay? And since this matrix is assumed full rank, we can solve uniquely for x0, okay? And as a consequence of this, since we can solve uniquely for x0 for the 0 input signal, u, that means that the system must be observable, okay? Since it seems like the 0 input response entirely characterizes my initial condition, right, because of this observability matrix rank condition, this means that this 0 input will distinguish between any two initial conditions out there, all right? So my system must be observable. All right, fantastic. And that's a proof. Okay, so let's kind of summarize what we set up here. what we had said is that this observability matrix, right, CA all the way down until CA to the n minus 1, gives us a complete characterization of observability on any interval that we want, okay? So, oops, let me change color and then talk about some remarks. OAC entirely characterizes observability, all right? And it tells us that on an arbitrarily small positive interval, we can kind of work out uniquely where our initial condition was, and observability follows from that, okay? So we actually get some even stronger conditions than observability, right? We get this unique reconstruction from any input signal that we want. Okay, so OAC entirely characterizes observability, right? So this gives us our desired algebraic conditions, right? This is pretty good, but, let's kind of think back to what we did in controllability, right? When we had derived this controllability matrix, which honestly kind of looks a little bit like this observability matrix, right? We'd said, okay, this CAB matrix is great, but it doesn't carry as much information as the Grommian, right? We had said that this Grommian, in the case of controllability, could kind of tell us a lot of nice information about how close to being uncontrollable we were, all right? Now, we don't really have any analog of this Grommian yet in the case of observability, right? So what are we going to do? Well, there's a really nice idea in control, which is that observability and controllability are actually dual concepts, okay? So this is kind of sketched out through this observability matrix versus controllability matrix, right? If I write out OAC equals CA to the n minus 1, then I write out my controllability matrix, CAB, which is equal to B, AB, all the way up until AN to the minus 1B. These things look really similar, right? It turns out this is no accident, okay? So it turns out what we can say is that a system is going to be observable if another system called the dual system is controllable, all right? So let me sketch out this idea in the following lemma. It was a really nice idea. It really tells us that observability and controllability are really two sides of the same coin, okay? All right, so what I'm going to say is A, C is an observable pair, right? Which just means that OAC is full column rank if and only if the pair A transpose C transpose is a controllable pair. Okay? So this means that the controllability matrix CA transpose C transpose is full row rank. Okay. So I say AC is an observable pair, which means that my state space system is observable if and only if A transpose C transpose corresponds to a controllable system. All right? So this is really powerful. All right? So it tells us controllability and observability are dual concepts. Okay? So you can actually formalize this notion of duality by defining something called a dual control system to any given state space representation. Okay? But I'm not going to go through that here. All right, so let me quickly give... There we go. That's better. My gosh. Let me quickly go ahead and give a proof of this result. All right? So the proof is essentially going to follow just directly from the observability and controllability matrices. Okay? So let's say suppose OAC is full rank. So let's say suppose OAC is full column rank. Then I have that OAC transpose is full row rank, right? Full column rank transpose gives me full row rank. All right. Now let's compute the transpose of the observability matrix. I have C all the way until CA to the n minus 1 transpose. If I work that out, then I get C transpose all the way until A transpose to the n minus 1 times C transpose. And what is this but the controllability matrix of C, A transpose, C transpose. Okay? But the result directly follows from there because, based on this discussion, this transpose is going to be full row rank. All right? The other direction follows identically to this. Compute your controllability matrix, take its transpose, conclude the observability matrix is full row rank. So here's a really, really nice thing about this result. So a nice result is we can immediately translate all controllability results to observability results. Okay? All we need to do is just apply this nice duality lemma, right? And then we can immediately conclude that all of our controllability things give us sharp characterizations of observability as well. All right? So let me show how we kind of port this over with the example of the Grommian. All right? So let's go ahead and define the observability Grommian using this duality idea. So definition, this is the observability Grommian. Okay, so let's consider a linear time invariant state space representation, right? Same as usual, A, B, C, D. And again, I'm just going to assume that there's a continuous time system just for the sake of this lecture. Then the observability Grommian. Observability Grommian is the map WO for observability from R greater than or equal to 0 to Rn by n. And this is defined as WO of t is equal to the integral from 0 up until time t, e to the a transpose tau, c transpose c, e to the a tau, d tau. Okay? And you'll notice all this is just the controllability Grommian with this dual system plugged in. Okay? So this is controllability Grommian with A transpose instead of A and C transpose instead of B. Okay? The reason we make this substitution is just exactly because of this duality result. All right? Okay. So now what we could do as a consequence of this duality theorem is we could say, all right, this observability Grommian actually gives us a sharp characterization of observability because we already know that the controllability Grommian gives us a sharp characterization of controllability. All right? So that brings us to theorem, which is the Grommian characterization of observability. Nice. Okay. So what we'll say is the following are equivalent for an LTI representation A, B, C, D. Okay? So again, a continuous time system. So point 1, this is going to be for any interval T0, T1, subset R with T0 less than T1. The system is observable. Okay, that's condition 1. Now condition 2 is the observability Grommian W0 of T is positive definite for any T greater than 0. Okay, that's condition 2. Now condition 3 will be there exists a time T greater than 0 at which W0 of T is positive definite. Okay? So this theorem effectively just takes the standard controllability Grommian theorem and it translates it directly to the case of the observability Grommian. All right? And the proof of this is just as easy as apply the duality lemma. And then the controllability Grommian theorem. All right? That'll directly give you a proof. All right? So I just want to quickly point out, I think this is something that I might have said out loud in the previous lecture, but maybe I didn't write down. It turns out you could show that if the Grommian is positive definite at any time, that implies that the Grommian is positive definite for all time. Okay, so that's where this equivalence between 2 and 3 comes from. Okay, very nice. So what we've just said is that we can actually get an equivalent characterization of observability using this observability Grommian, right? This is going to be one-to-one with this controllability Grommian. And now the nice thing is, like we had said last time, is the observability Grommian carries much more information than the observability matrix OAC. Okay, so it gives us much more than a simple yes or no test for observability. Okay, so more than a simple yes/no test for observability, right? Its minimum singular value tells us how close to unobservability we actually are. All right, so this carries a lot of valuable information. Now, you'll find on your homework assignment for this week that the observability Grommian and controllability Grommian actually lead to a really nice form for system analysis called the balance realization. Okay, so there's actually a lot of applications of these things in like model reduction and all these other classical problems in control theory. Okay, fantastic. So before we move on and talk about some kind of system decompositions that have to do with observability, I want to talk really briefly about how we can compute this observability Grommian with a Lyapunov equation, right? Remember in the case of the controllability Grommian, we said, okay, due to the form of the controllability Grommian in the infinite horizon case, we can directly compute it using a continuous time Lyapunov equation. Now I just want to say that we do the same thing for the observability case. All right, so I'm going to state another theorem, which is CTLE computation of the observability Grommian. Okay, so what this says is consider system representation A, B, C, D, where A is Hurwitz, right? Remember that means A has stable eigenvalues such that x dot equals ax is globally exponentially stable, right? All the real parts are less than 0. Then the infinite horizon observability Grommian is defined as follows. So it's defined WO equals the limit as t goes to infinity of WO of t equals the integral from 0 up until infinity of e to the a transpose tau, c transpose c, e to the a tau, d tau, right? We're just taking the limit of the Grommian. Then we have that W naught is the unique solution to the continuous time Lyapunov equation. A transpose P plus PA equals minus C transpose C. And further, W naught being positive definite is in fact a sharp characterization of AC observable. Okay, I just want to give a quick proof sketch of this because I think I went through it a little bit quickly last time. Okay, so first what you have is that the fact that it is a solution follows directly from formula for solution to CTLE. Okay, so if you look back to our Lyapunov lecture, then you'll find that, this over here is exactly the form of the solution to the CTLE. Now, why is this being positive definite, a sharp characterization of observability? Well, we have that if the limit of t goes to infinity of W naught of t is positive definite, then there exists a t such that W naught of t is positive definite, t greater than 0. Okay? And then this from above implies AC is observable. All right? Now, going in the other direction, you can kind of make a similar argument. Okay? All right. Fantastic. Great. So what we've done is we've come up with a couple of really nice, sharp algebraic characterizations of observability, right? Kind of using this duality theorem, we found that we could really say all of the same things that we could for controllability. All right, fantastic. What I want to do next is I want to talk about some basic decompositions and detectability. So now that we know that observability and controllability are kind of dual concepts to each other, right? You'll kind of remember that all the way at the end of last lecture, we talked about a weaker form of controllability called stabilizability, right? So what we effectively said was, okay, oftentimes, maybe controllability is too strong of a condition, right? But if the uncontrollable piece of our system is already stable, maybe that's going to be okay for us, right? If stabilization is the thing that we're interested in, okay? So now we're going to just kind of come up with an analogous concept for observability, right? What we're going to say is that, all right, if the pieces of our state which we cannot observe, right, which we cannot reconstruct from data, is already stable, then maybe things are going to be okay for us. Okay, so this is what leads to the concept of detectability. So we're going to follow the same path as before, right? First, we're going to show that we could split up our state space into an observable component and an unobservable component. Then after we do this, we're going to go ahead and show how we could use that fact to decompose our system. Okay. All right. So how to construct a decomposition into observable and unobservable pieces. Well, in order to figure this out, let's take a look at that equality which we kind of had set up earlier, right? So we had y of 0, yn minus 1 at 0 is equal to OAC times x naught when we take the input u to be equal to 0, okay? So here's the basic idea. The idea is we have, if a state x naught is in the kernel, right, or null space of OAC, then it's not going to be observable, right? Because anytime we have something in the null space, there's automatically non-uniqueness, right? We won't be able to uniquely reconstruct what that vector was, okay? So using this idea that the kernel of OAC represents states which we cannot uniquely reconstruct, we can define something called the unobservable subspace of our system. And then by taking the orthogonal complement of that, we can define the observable subspace of our system. All right, let me go ahead and do that. So definition, this is the observable / unobservable subspace. Okay, so let's consider an LTI system representation, which we'll call A, B, C, and D. Now first, what I'll do is I'll define the unobservable subspace. So the unobservable subspace is defined as the kernel of OAC, right? This is a subset of our state space, Rn, right? Because OAC is mapping from Rn into this output space. Okay, so that's the unobservable subspace. Now two, the observable subspace. Observable subspace is its orthogonal complement, okay? OAC perp. All right, fantastic. So you might remember that, when we did this kind of analogous definition for controllability, what we had shown was that the controllable subspace was A invariant, right? But we had defined the controllable subspace in terms of the range of the controllability matrix. Here we're using kernels, right? So instead of saying that, the observable subspace is A invariant, what I'm going to say is I'm going to kind of flip it, and I'll say that the unobservable subspace is A invariant, okay? So that brings us to lemma, which is the unobservable subspace is, let me just rewrite it out, kernel of OAC is A invariant, okay? So that means that if we take a vector v, which belongs to this kernel, and we multiply it by a, then a times v will still belong to this kernel, all right? And the proof of this is just apply Cayley-Hamilton. All right, so I'll leave the details for you for the sake of time, okay? Really same deal as the controllability one. Okay, so using this property that this unobservable space is A invariant, we'll find that the observable subspace and unobservable subspace really split our space up into nice components, okay? Once more, these components will respect the dynamics of the system. So that leads us to this proposition, or theorem, which is the observability decomposition. Okay, so let's consider an LTI system with A, B, C, D, A and Rn by n, okay? Now let's say, suppose the observable subspace has dimension k, which is less than n. Then there exists a transformation matrix T, which belongs to Rn by n, such that T inverse AT is equal to A observable hat, okay, A21 hat, A unobservable hat, 0, okay. T inverse B will equal to B observable hat, B unobservable hat, and finally C times T will equal to C observable hat and 0, okay? Now further, what we're going to have is that the pair A observable hat, C observable hat will be observable, and we'll have that the size of A matches the dimension of our observable space, okay? So A naught hat belongs to RK by K. Okay, fantastic. So what we're saying is we could split our system into an observable component, right? And then an unobservable component, right? And we see that this unobservable component doesn't even show up in the output, right? So there's no way that we could reconstruct the unobservable component. That kind of makes sense from the standpoint of the observability decomposition. Okay, so I'll just very quickly outline the proof. So the proof is identify a basis for your unobservable subspace, okay, cur of OAC, okay. Now we'll do the same thing for cur of OAC perp. So we put these basis vectors into the columns of the matrix T. You apply invariance, and then you apply the fact that these first couple columns of C will in fact belong to this observable piece, and then the result follows from there. Okay. So in order to show that this pair A naught hat, C naught hat is in fact observable, what you would do is you would compute the observability matrix associated to that. Okay. So the details of this will be in the notes. Just for the sake of time, I won't prove it here. Okay. So now, using this idea of the observability decomposition, right, which really precisely splits our system into an observable part and an unobservable part, we could say what it means for the system to be detectable. All right, so you can think of detectable as the observability analog of stabilizable. All right, so let's define this. So that's not a theorem, that's a definition. So definition, detectable. So we say that a pair AC is detectable if its unobservable part, A hat unobservable, is Hurwitz. Okay? So the basic idea is if the part of the system which we cannot see, right, which we cannot observe is already stable, then our system will be detectable. All right? So I want to make just a very quick side comment that I didn't make last time, which is remark is that a unobservable hat is not necessarily unique. Okay? And this is a result of the fact that this decomposition over here is also not necessarily unique. Okay, we can really kind of permute all of the columns in like a unobservable hat, for instance, right? And we can kind of shift these things around a little bit. But the nice thing is that detectability doesn't depend on the particular observability decomposition. Okay, so you could show that if it holds in one observability decomposition, it'll hold in all of them. And this is really a consequence of the fact that eigenvalues are kind of preserved under similarity transforms. Okay, so I won't prove that here, but this is just something to keep in mind. All right, this makes sure that detectability is in fact a well-posed definition. Okay, so all the way at the end of last lecture, I stated this test for controllability, or this test for stabilizability called the PBH test, right, for Popov, Belovich, Haudas. Now, due to duality, we could do the same thing for observability and detectability. Okay, so this is PBH test for detectability. And what this says is that the pair AC is detectable if and only if the rank of SI minus A and C equals N. And this should hold for all unstable values of S and C, okay? Such that the real part of S is greater than or equal to 0. Okay, this basically scans over all possible unstable eigenvalues of A, and if we get a rank drop at that point, then that means that we'll lose observability at that point. Okay, so the proof of this will follow from duality and the controllability theorem. Okay, now you can also get a direct proof of this result using this observability decomposition up here. Okay, so the details of that will be in the notes. If you're interested, I suggest you go check it out, but just for the sake of time, we won't be able to cover it here. All right, so I want to talk about one more decomposition, and then I promise I will kind of stop listing things, and then we'll start talking about some more interesting things again. All right? Okay, so the nice thing is we can actually put the observability and controllability decompositions together, okay? So we can kind of combine this controllability decomposition from last time, right? Which split up our space into into a controllable component and an uncontrollable component. And then this observability decomposition, which we just talked about above, which splits our system into observable and unobservable, we could put these two things together to identify a space which is entirely controllable and observable, right? One which is controllable but not observable, one which is observable but not controllable, and then one which is neither controllable nor observable. All right, so that's a pretty bad space. So let's go ahead and state this theorem. Again, I'll state it without proof, but essentially it just follows from some kind of careful bookkeeping and applications of the controllability decomposition and observability decomposition theorems. This is called the Kalman canonical decomposition. All right, so this is the same Kalman as the Kalman filter, right? He was a very busy guy. Okay, so let's consider an LTI system, A, B, C, D, our favorite. Then there exists a transformation T in Rn by n, for which T inverse AT will be split into A controllable and observable hat, okay? A21 hat, A controllable but unobservable, 0, Then we'll have a hat uncontrollable but observable, a 0, a hat 4, 3. And then finally in our bottom corner, a hat uncontrollable, unobservable, the worst. And then we'll have some extra blocks up here, okay? So, and then over here, we'll have 0, 0, 0, 0, okay? Now, B will kind of split up similarly, so we'll have T inverse B will be split up into a B hat controllable and observable, B hat and controllable but unobservable. And then in our bottom half, right, because we have all of the uncontrollable pieces in this half, we'll just have both zeros, right, because no control input appears in there. Then we'll also have C times T equals C hat, controllable and observable, right? And this is non-zero because our controllable and observable piece is over there. Then we'll have a 0, right, because our second block is not observable. Then we'll have a C hat uncontrollable and observable, right, because our third block is observable. And then finally we'll have a 0 because our fourth block is not observable, okay? So you can kind of keep track of what each block of these is doing, right? So we have this one, which is really our ideal block. This contains everything with, you know, all the nice properties we could want, right? And then all the way at the end over here, we have the worst block, which is neither controllable nor observable, right? So we really hope that that doesn't exist. Okay. So here, like I said, CO is controllable and observable, okay? So we have ACO hat, BCO hat is controllable pair, and ACO hat, CCO hat is an observable pair, and so on, okay? So on. All right. So the proof is just careful bookkeeping plus controllability and observability decompositions, okay? So there's a couple more arguments that need to be made with respect to invariance, but this is really the gist of the idea, okay? So again, this will be in the notes. All right, fantastic. So we're gonna kind of leave up our basic discussion of controllability and observability over there, right? So what have we done? Have we met all of our goals? Well, I think we did a pretty good job, right? We kind of went out seeking these really nice, sharp algebraic characterizations of controllability and observability, and we found both of them, right? And what's more, we found really a number of ways to do that, right? We have these Gramian methods, which were, you know, they carry a lot of information, but, you know, maybe they're, I don't know, a little bit harder to compute. And then we had this matrix method, right? Controllability matrix and observability matrix, which is super easy to compute, right? We just kind of compute a couple matrix powers, stick them together and find a rank, but they give us less information, okay? So there's a kind of nice trade-off that we found there. So what's next? What do we do? Well, next I want to talk about something which really might initially seem a little bit unrelated to this idea of controllability and observability that we've been doing, but it turns out controllability and observability are actually going to be like really fundamentally wrapped up in this idea, okay? It's going to be our final point for today. So point 3, which is about minimality. Okay. So I want you just to bear with me for a couple minutes, right? I promise I'm going to bring this back to controllability and observability. I'm just going to sketch out what the basic idea of minimality is, and then we'll kind of see if we can characterize it using some of the concepts that we've talked about in this lecture. Okay? All right. Great. So here's a scenario. We know that, you know, when we're talking about the input-output perspective on control, what we're often interested in is the zero-state response, right? So I want you to imagine a scenario where I hand you a map, right, and I claim that this map is kind of like the zero-state response map of a system, okay? So let's say I hand you a map. Let me call it rho naught. And let's say rho naught takes in a pair of times, t1, comma t naught. T1, t naught, and it takes in an input signal u, and then it returns some output signal y at time t1. Okay? So let's say I claim this map is the 0 state response of a system, okay, on some input space u and some output space y. All right? Now what I want you to do is I want you to figure out what state space system corresponds to this map, okay? So what state space system representation, right, if any, corresponds to a 0 state response, of rho naught, right? And a couple of questions might initially jump to mind, right? First, you might ask, is this unique, right? Is there only one state space system that does this? Probably not, right? Now, a second question we might ask is, let's see, is there a smallest state space system that does this, right? A state space system with the smallest possible state dimension that still gives me this IO map, okay? So this is what the idea of minimality is, okay? So there's some kind of abstract 0 state response map that's out there. Now what you do is you construct a state space representation that corresponds to that 0 state response, okay? So that's called a realization of this response map. And then a minimal realization is going to be the realization of rho naught with the smallest possible state dimension, okay? So let's do a little bit of work on, kind of putting mathematical language down to this idea of a realization and, a minimal realization, an equivalent realization, so on and so forth, okay? So let's talk about this in the context of state space representations. So let's talk about state space representations, okay? And how they relate to this idea of realization. Okay. So what do we know? We know that the 0 state response of state space representation A, B, C, D is computed as follows. Well, it's computed integral from 0 up until t. Let me just write this out. Rho of t, 0, 0, and some input signal u, right, equal integral from 0 to t of c e to the a times t minus tau, bu of tau. Can't write today, it would seem. Bu of tau, there we go. D tau plus d times u of t, okay? So if we want to figure out what, the smallest state space representation is corresponding to a given response, right? Maybe it makes sense that, we kind of characterize what it means for two 0 state responses to be equivalent, okay? So this leads us to the idea of an equivalent realization. So the basic idea of an equivalent realization is it's going to be, we're going to declare two state space representations to be equivalent realizations of some 0 state response, just if they have the same 0 state response map, okay? It's pretty straightforward. So definition, this is an equivalent realization, okay? So we say that two state space representations, A1, B1, C1, D1, and A2, B2, C2, D2 are equivalent realizations if they have the same 0 state response. Okay? And based on what we said above, this effectively boils down to the following holding for all times and for all inputs. So C1 e to the A1 t minus tau, B1 u of tau d tau plus D1 u of t should equal to the integral from 0 to t of C2 e to the A2 t minus tau, B2 u of tau d tau plus D2 times u of t, okay? So this should hold for all inputs u and times t. Okay? All right, so this is what an equivalent realization is, right? If we're saying that, realizations of this abstract map rho naught are, state space representations whose zero state response corresponds to that map, then two realizations are equivalent if they have the same zero state response, okay? So how do we actually go ahead and characterize an equivalent realization? Well, let's think about this for a moment. So what do we need for two realizations to be equivalent? Well, if we go ahead and we evaluate this expression at time t equals 0, right, then this entire integral term will disappear, okay? So it kind of seems reasonable that first we need d1 times u is, or u at time 0 equals d2 u at time 0 for all u of 0 in Rm, okay? So this is going to be the same thing as d1 equals d2. Now second, if we go ahead and we apply a unit impulse input to both of these systems, right, and we evaluate that at this time t, then what we'll find is that we'll need c1 e to the a1t is equal to, missing a times b, is equal to c2 e to the a2t times b2. And this should also hold for all t, okay? But can we get a simpler representation of the second condition? Well, sure, right? By Cayley-Hamilton, we know that if we can get, something that kind of looks like this, only holding for a couple of powers of a, then we can get it holding for e to the at as well, right? So that leads us to the following proposition on equivalent realizations, okay? So proposition, equivalent realizations. Okay, so we say that the state space representations A1, B1, C1, D1, and A2, B2, C2, D2 are equivalent realizations, actually if and only if the following two things hold. So one, we require D1 equals D2, like we had said above, and two, we require this Cayley-Hamilton base condition, which is C1 a to the k times, or excuse me, A1 to the k times B1 equals C2 A2 to the k times B2, okay? We can request that this holds for all k greater than or equal to 0, but by Cayley-Hamilton, we know we can actually only check this for the first n minus 1 powers, where n is going to be the larger of the dimensions of A1 and A2, okay? All right, so the proof is the same as the idea sketched above, okay? So first we evaluate the zero state response at time 0, and then we can consider the response to an impulsive input. That kind of gives us one direction, right? And the other one follows from this Cayley-Hamilton argument, okay? All right. So again, I'll include a more detailed version of that in the notes. Just for the sake of time, we can't do it here. Okay, so these are some nice conditions, right? So the conditions C1 A1 to the k B1 equals C2 A2 to the k B2 give a nice way, and also D1 equals D2, nice way to check equivalence, okay? This is a sharp characterization of equivalence. So, kind of because these things are a little bit important and they tend to show up, these parameters actually have a name, okay? So we say that the powers c a to the k times b, where k equals 0 up until time n minus 1, are called the Markov parameters of A, B, C, D, okay? So these Markov parameters entirely characterize whether we have an equivalent realization, okay? In addition to the fact that D1 equals D2, right? So these uniquely determine whether a given realization will be the same as another one. Okay, so using these ideas of equivalent realizations, and now this nice characterization in terms of these Markov parameters. Right? Markov parameters. We can state a nice definition for a minimal realization. Okay? This gives us definition, which is a minimal realization. Okay? So we say that a state space representation, A, B, C, D, is called a minimal realization if there is no equivalent realization with lower state space dimension. Okay? So let's say, I have a state space representation A, B, C, D, and the dimension of the state space is 3. If I can find an equivalent realization with a state space of dimension 2, then my original representation was not a minimal realization. Okay? Now, if on the other hand 3 was the smallest dimension you could go, then it would be minimal. Okay, so above we have, kind of this characterization in terms of Markov parameters of whether two things are going to be equivalent or not, right? So my question is, when is a representation minimal? Right? Maybe we can get some sort of answer with these Markov parameters, right? Well, let's take a look at the terms CA to the K times B, right? So these show up in our observability matrix, right? Now, on the other hand, these terms A to the KB, these show up in our controllability matrix. This is kind of interesting, right? Maybe something's going on here. So there seems to be some connection between minimality, controllability, and observability. Okay? So something's kind of happening, right? So let's kind of sketch out a couple examples to see if we could figure out what's really going on. So let's consider an example. So I want to give you a system that is uncontrollable and unobservable, all right? And I'm going to ask you if that system is a minimal realization. So let's go ahead and consider the system x dot equals, let's say, 1, 0, 0, 1, x1, x2. Sure, I'll just write out the full state over here. x1 dot, x2 dot equals, plus 1, 0 times u. And then let me take y equals 1, 0, x1, x2. And my question is this minimal? Take a moment to think about it, okay? So if we go ahead and we kind of multiply out these Markov parameters, or you just kind of use your basic intuition, you'll find that this is not minimal, right? Because the output response to the system only actually involves x1, right? So no. So zero state response will only involve x1 terms, right? So now let me give you another system, which is just the x1 component, right? So I'll take x1 dot equals x1 plus u, and then y equals x1. Now this, on the other hand, is minimal, right? We can't go any smaller than this. So this is minimal. Now there's some really interesting things going on here, right? So our larger system, you can kind of tell by inspection, this is not controllable or observable. Okay? Now our smaller system is controllable and observable. Okay? So in kind of the scope of this Kalman decomposition that we just mentioned earlier, we can actually find this smaller system by picking out the controllable and observable component of our larger system. Okay? So it turns out this idea of minimality is really tied up in controllability and observability. All right? So let me go ahead and state a theorem which kind of summarizes these ideas, right? And then we'll kind of lead things off for the day. All right, so this is theorem, which is controllability, observability, and minimality. Okay, so I'll say consider an LTI state space representation, A, B, C, and D. Okay. Now first, if either A, C is not controllable, or excuse me, not observable, or A, B is not controllable, then the representation is not a minimal realization. Okay? Now, on the other hand, if AC is observable and AB controllable, then it is a minimal realization. Okay? So it turns out that controllability, observability, and minimality are actually kind of all sharp with each other, right? Your system representation will be minimal if and only if you get a controllable pair and an observable pair, all right? So the proof it kind of follows from similar ideas to those outlined in the example above, okay? So you can see the notes for the full proof of this, all right? Okay, fantastic. So before we finish, I just want to talk about one more detail, which is how this idea of minimality relates to transfer functions, right? So let's recall, where do transfer functions come into this? Transfer functions. So remember, the transfer function is the transform of the zero state response to an impulse. Okay? And what we found is that it characterizes all system responses, right, to any input out there. Okay? So in this light, it kind of makes sense to talk about a realization of a transfer function. Okay? So if I give you a transfer function g hat of s, then a state space representation A, B, C, D is a realization of g hat if the transfer function c si minus a inverse b plus d equals g hat of s. Okay? So remember, this is kind of this state space to transfer function characterization, right? c si minus a inverse b plus d is equal to the transfer function corresponding to the system. Okay? So if, in fact, the transfer function of the state space system gives us g hat of s, then the state space representation is a realization of the transfer function. So what the above tells us is that a minimal realization of a transfer function is one that's controllable and observable. All right? Now, the really fundamental idea is when we perform this, kind of multiplication, c si minus a inverse b plus d, remember what we said before is that, we kind of cancel terms out until this is in simplest form when we're computing the transfer function, right? So it turns out any terms that we cancel are kind of redundant information, right? So if I give you a transfer function s plus 1 times s plus 2 over, let's say, s plus 3, s plus 4 times s plus 2. This s plus 2 is redundant information. Okay? So what this indicates, the state space representation was not minimal. Okay? So, if I compute c times si minus a, b plus d before simplifying it, and I get this s plus 1, s plus 2 over s plus 3, s plus 4, s plus 2, and these factors cancel out, right? If there's common poles and zeros in this transfer function, then that means that my state space representation wasn't actually minimal, right? It carried extra information that didn't end up showing up in the final transfer function, all right? So this idea leads me to the final theorem for today, which is controllability, observability, and cancellation. Okay? And what this effectively says is that for a transfer function g hat of s and a state space realization a, b, c, d, the realization is minimal if and only if a, b is controllable and AC is observable. Okay? Now further, lack of controllability / observability leads to cancellation of factors in C si minus A inverse B plus D. Okay? Because when these factors cancel, they no longer show up in the output of our system. Okay? So we're going to leave things there for today. Thanks for watching.